they can transfer energy to the adjacent atom by vibrating about its mean position and making collision with the adjacent, and thereby the energy is transferred. Whereas if we supply a little more energy, then it will transform into liquid. Liquid molecules can enjoy little more freedom. They can go from one place to other place. Of course, how much energy you are supplying depend on that also. And further, if you supply energy to water, you will get water vapor. It's a gaseous state, and the distance between molecules or atoms in gaseous phase is quite large. There we also define mean free path and all those things. And gases are characterized by certain kinetic theory of gases. Those laws are there. Further, if we give energy either in the form of electrical energy or heat energy sufficiently, then these gas molecules are ionized. Once they are ionized, they don't follow typical laws which are there for gases, and therefore plasma is labeled as a fourth state of matter and cannot be considered as a third state, as a gaseous phase. Here, gas is essentially non-conducting. However, when sufficient high electric field is applied or a temperature is increased, the ionization occurs. Means what happens basically is that under the influence of electric field, outermost shell electron is liberated, thereby forming an electron and an ion. So normally plasma is a quasi-neutral. The meaning is that you have equal number of ions and electrons. However, there are cases, there can be doubly ionizable atoms. So in those cases, slightly the number of electrons would be more than number of ions. But then this is conducting gas. That is the plasma. Next, as far as energy is concerned and the temperature is concerned, this slide shows that the plasma temperature is in the range of 10⁴ to 10⁵ Kelvin, and the energy of plasma species in the range of 1 to 10 electron volt, which is quite sufficient to carry out many chemical reactions and surface modification of materials. So very apt energy is there with plasma. Next. Now plasma can be classified into two categories: thermally equilibrium plasma. It means that whatever plasma species are there, electrons, ions, some neutrals, atoms, molecules, whatever is, all those plasma species will have equal temperature. So thermal equilibrium. The reason behind it is at high temperature the gas becomes fully ionized and sufficient number of electron neutral inelastic collision occur, and hence the energy of electrons is distributed or transferred to all other plasma species, and therefore here you can see that T suffix E is electron temperature, which is equivalent to T suffix I ion temperature, and this is called as a hot plasma, which is used in nitriding, spray coatings and cutting, drilling of metallic plates and all those things. Next. Whereas cold plasma, that is thermally non-equilibrium, in this case only 1 to 10% of gas molecules are ionized, and there is insufficient inelastic collision between electrons and other plasma species, and because of that there is not efficient transfer of energy from electrons to other plasma species, and hence the electron temperature remains high and all other plasma species temperature is around room temperature only. Now here the electron temperature is 10⁵ Kelvin, which is very very high as compared to T suffix I, that is ion temperature. So overall, and the size of electron is 2000 times less than that of ion, and therefore we don't feel that the temperature is so high because the size of electron is so small, and the overall temperature of plasma is around room temperature, so it is called as a cold plasma. Because the other type of plasma where the temperature is very high, it can melt metals and all, so the comparison to that, this is cold plasma, and this cold plasma can be generated using high DC voltage or radio frequency power supply, glow discharges, neon sign lamps that you must have seen, right? Uh, then ionosphere, aurora observed on the polar region. Atmospheric pressure glow discharge is also created, where one of the electrode at least need to be covered with dielectric material. Otherwise, if it is not covered, as soon as the plasma is strike, gas becomes conducting, and then there will be there is a possibility that tremendous current may flow through plasma, and the power supply will stop operating or will get burned. So dielectric barrier discharge is that type of, like corona, microplasma, plasma torches are there. Now plasmas are used. These plasma pictures which are shown here are tissue tolerable plasma and can be used in wound healing and medical devices, medical applications. Next. In order to functionalize nanomaterials, what we have done is we have developed 360-degree rotating plasma reactor, where nanoparticles are put in the tubular reactor, and to that tubular reactor we have created three protrudes so that nanoparticles are taken up and then they freely fall in the plasma zone in the rotation, and particles are equally treated. Next, this is actual photograph of our 360-degree plasma device. Next, here electrodes are externally applied. Go back. Now click on the first. You can see that glow discharge is the plasma. It's a tubular reactor and it is rotating reactor. So the bearings which are used, okay, are vacuum tight and yet is capable of rotating. That's the critical part of it. The vacuum level is also maintained. And in the second diagram, the rotation is stopped, but you can see the flickering. That is the pulsing nature. So for certain millisecond plasma is on, and for certain millisecond plasma is off. That flickering and protrude you can see at the center portion. So that helps in us to take these nanoparticles up, and then they freely fall in the plasma zone. Okay, with every rotation. Next. So what happens when we put any polymeric material, for example polyethylene, in the plasma environment, energetic species interact with the surface of substrate material. There will be a bond breaking because plasma is having around 1 to 10 electron volt energy, which is sufficient to carry out such modifications, and thereby creating free radicals, functionalization, attaching some group like OH group and all those things, and then through such functionalized material, okay, it can interact with the surrounding in a better fashion. Next. Plasma finds application in variety of fields, even including food processing, light sources, optics, information technology, printing technology, chemistry of new materials, biomedical engineering, electronic engineering, tissue engineering, automotive industry, packaging, textile industry, and so on and so forth. Next. So here, this diagram depicts how nanoparticles are functionalized. It means that certain specific functional groups are attached onto the surface of nanomaterials with the help of plasma. We can attach carboxylic groups or amine groups or OH groups, halides, epoxy, and then such functionalized nanomaterials can find applications in spintronics, nanocomposites, biosensor, targeted drug delivery, dielectric films, cancer therapy. So, attractive features of plasma surface modification is that these are the advantages, that plasma can modify only top surface layer, just few layers, whereas the bulk property remain unchanged. That's the beauty of it. It is a single step, all dry process to minimize waste. So it means that it is environment friendly process, applicable to virtually any solid surfaces or even nanoparticles with 360-degree rotating reactor. The modifications which are carried out are highly conformal, highly cross-linked, and pinhole-free film can be obtained with the help of plasma polymerization, and we can have excellent control over film thickness. Whatever nanometer we want, we can have that specific. And wide range of film chemistry is possible with pulse plasma. Next. Traditionally, people try to vary various plasma parameters, like by varying system pressure, by changing gas or monomer flow rate, varying power or distance between two electrodes, time of treatment, substrate temperature, or by giving some certain voltage to the substrate called as a substrate biasing, okay, or changing substrate location in the plasma zone itself. So with these parameters, the achievement in surface chemistry variation was something in delta x was a very limited one, but with our approach is variable duty cycle pulse plasma, where we can vary surface chemistry widely. So that's the beauty of pulsing nature of a plasma. Next. Why surface chemistry is very important? Why people are talking about we need to modify surfaces, even implants, whatever is, right? So material is selected on the basis of its mechanical property for any implant, but not necessarily that its surface is suitable. Surface needs to be biocompatible, then only our body will accept. So you need to modify its surface. And that is why, and there are so many applications where surfaces play very important. Material interact with surrounding with surfaces only. So surface, even when we go to buy some material, okay, we look at the texture of the fabric and all those things. So surfaces play a very important role everywhere. Okay, sometimes we need hydrophilic surfaces, sometimes we need hydrophilic phobic surfaces, or even moderate in between. For biomolecule immobilization, blood compatibility, cell growth, drug delivery, biosensors, tissue engineering, in all these fields, surface chemistry plays very important role. And if you modify surfaces of materials using chemical treatment, then the residual chemicals would interfere with the property. Whereas this plasma processing, if it is just any kind of gas is used, okay, there is no question of pollution of water or residual chemicals, and therefore this modification of surface chemistry using plasma processing has an edge over other traditional ways of modification of materials. Now coming to the pulsing nature. Plasma is kept on for certain time period and certain time period off, and this on and off period width can be varied independently. So the square wave pulse that you see indicates plasma on period and off period. Now when the plasma is strike, that is the on period is there, that time plasma species starts to generate, goes to the saturation, that you can see, and in the off period, even though the power is not given, but still plasma species, active species are there in the plasma reactor, and they carry out whatever the reaction is there, either surface modification or deposition on the substrate. But then its population slowly, decreases. The next pulse should arrive before all the active species, okay, are disappeared in the plasma region. So there, you have to have certain things that you can play with on and off time suitably, so that the maximum deposition rate you can achieve by keeping suitable off time. So period is T on plus T off. The one cycle is the period, and duty cycle is plasma on period divided, plasma on time divided by period. So duty cycle is T on divided by T on plus T off is the duty cycle, and the effective power is power W. Effective is the total power in watt into the duty cycle is the effective power. So the effective power requirement in pulse plasma is less as compared to continuous wave plasma. Now here is the example, the equivalent wattage in pulse is plasma on time divided by plasma on plus off time into peak power. If you consider a pulse of 10 millisecond on and 50 millisecond off, then on plus off time will be 60 millisecond, on time is 50 millisecond, and 150 watt peak to peak power is given, and if we put those values, okay, it comes out to be only 25 watt effective power. So the power requirement, the consumption is also very less. Now here is the deposition characteristics. For some purpose I wanted to have a film having more bromine content in that. So the deposition, the figure shows the thickness of film deposited for 10 minutes as a function of off time. As we increase off time, you can see that the thickness of deposition increases and then there is a peak. This increases because if we use continuous wave plasma, that is 0 point that you can see on the x-axis, the deposition rate is around 30 nanometer, okay, in 10 minutes. So in case of continuous plasma, it's a competitive ablation and deposition process. So ablation and deposition is simultaneously, whereas in the off state, basically that is the essential time where these active species get settled down on the surface. So the deposition rate in case of off time increases, and therefore as we increase off time, you can see that there is an increase in deposition rate. However, after you can see that 50 millisecond off time, then there is a decrease in the deposition rate. The reason is the next pulse appeared after a sufficiently long time when there were no active species in between. So if that is the case, then again the deposition rate will decrease. So it means that you need to have off period tailored in such a way that before all the active plasma species are vanished from the plasma regime, the next pulse should arise, then you get a very good deposition rate. Also, these are AFM pictures, continuous wave plasma, and this 10-10 pulse that you will find the surface is little rougher because simultaneously itching is also there along with the deposition, but deposition is predominant. Whereas as we increase off period, that 25 millisecond off and then next is 50 millisecond off, 10 millisecond on period is kept constant. So as we increase off period, so whatever the species, okay, they get sufficient time to get settled, even the lateral movement on the substrate also, and because of that the surface is now quite smooth. So not only the surface chemistry but also surface morphology can be tailored precisely with the help of pulsing nature of plasma, which is not possible with continuous wave plasma. Next. Now here is an example. We wanted to have a good number of hydroxyl groups, OH groups on the surface for certain application. So what we did, we selected allyl alcohol as a precursor monomer and resulted into polyallyl alcohol film on the substrate. So the lowest in FTIR diagram you can see the lowest one film was deposited for the pulse 1, 2. 1, 2 means 1 millisecond on, 2 millisecond off. There you can see that the red portion in FTIR diagram is assigned to CH. CH is basically hydrocarbon responsible for hydrophobic nature, and where OH is responsible for hydrophilic nature. So for the lowest FTIR diagram, OH groups are minimal and the surface is quite hydrophobic. Then we changed pulse from 1 2 to 1 5, means 1 millisecond on, 5 millisecond off. So here as we go on increasing off period, in this experiment we have kept on period 1 millisecond constant and off period varied from 2 millisecond to 30 millisecond, right? So as we go on increasing off period, the further fragmentation of monomer is avoided. So retention of monomer functional group is more and more as we increase off period, right? And because of that, here the concentration of OH that is shaded in blue part is increasing as we increase off period, and the concentration of CH is decreasing, so that you can see. So, and then to quantify the extent of surface modification and extent of the hydrophilicity created, we measured contact angle, and then you can see that the contact angle is reported as a function of off time. As we increase off time, contact angle decreases, means the water droplet is now getting flattened on the surface, is more interacting with the surface, is more wettable. That is what it is. So we use pulse plasma polymerization technique to systematically vary the chemistry of plasma polymers. And here you can see that the sequential change, the duty cycle was systematically varied. The sequential change in duty cycle leads to large scale progressive change in film chemistry. And such large scale change in film chemistry is not possible just by varying distance between two electrode, or varying power, or varying some other plasma parameters. And this we could achieve because of the pulsing nature of the plasma. We could retain good number of monomer functional group, in this case OH group, on the substrate. Next. I happen to work with this Evan Clark company for developing enteric coating on nano micron size particles using pulse plasma. So, what is enteric coating? Enteric is basically a small intestine, and this is a coating offered on medication, that is drug, in such a way that this drug is directly delivered to the intestine. So of course it will go through stomach, but when that goes through stomach, that coating will remain intact, and when it goes to the intestine, that coating will be removed, and the drug is now available for intestine to absorb. So that is called as an enteric coating. So basically this coating, you can say that it is a pH sensitive coating. When the pH is around 2.5, which is the pH of stomach, is a harsh acidic medium, that way the coating remains intact. And as soon as these drug particles go to the intestine, where the pH is changed, it is relatively basic or less acidic, 5.5 is the pH around that, in intestine, the coating disintegrates and the drug is available for intestine to absorb. Next. Why enteric coating is required? There are three reasons. To protect stomach from the drug, particularly non-steroidal anti-inflammatory drugs cause or hamper lining which is there on the stomach and can result into ulcer. So that is not a good thing. So it is not advisable to take painkillers without the prescription of doctor, without the advice of doctor. Otherwise, it may lead continuously. If you go on taking painkillers, it will cause ulcer, stomach ulcer. So this is the effect of medicine on the stomach. Stomach lining gets hampered. Then another reason, to protect drug from the stomach. Sometimes stomach acid and some enzymes present in the stomach can adversely affect and interact with the drug, causing discomfort, nausea. So that is also possible. This omeprazole is a drug. It stops producing acid, when taken. That should be delivered into the intestine for better effect. It is destroyed to some extent in the stomach. So such drug needs to be protected from the stomach. So both ways, there are category of drugs, they affect on the stomach. There are some category of drugs, they are affected by the stomach acid and the enzymes present in it. So in both the cases you need to have enteric coating. And the third one is to release the drug, or here I say supplementary whatever you take after the stomach for cost effectiveness. sometimes, you know, doctor advise to have some protein powder or some, nutrients to have. But if some medications or nutrients or supplementary, whatever is advised, if it is getting affected in the stomach acid, and say 70%, 60% of that is getting affected, so what you are getting 30%, 40%. So the bioavailability is a question mark. So the bioavailability is 30 and 40%. If you are paying $100, so effectively you are getting only 30-40 bucks material. That's it. Because other material, that percentage, okay, is what we say, degraded by stomach acid or whatever it is. So, and
you mean the drug which is encapsulated in certain coating. That coating get open according to the environment it gets.
Yes, that is what it is.
If such an environment it goes on the journey rather than reaching the destination, it may be something catastrophic.
Yeah. So basically these are pH sensitive coating.
Yeah.
So whatever is the pH of stomach and plus or minus something, that the coating will remain intact. As soon as it reaches to the intestine where the pH is different, so for that pH, that coating will get disintegrated, removed. That is the basic idea.
That we agreed, we accepting that the sequence of pH will be as.
Yeah, that is studied.
If something plus or minus happens, it may break.
Yeah. So nowadays, you have capsules available, enteric coated capsules, or enteric coated tablets are also available. So what happens is that this tablet or capsule intact goes till the intestine, and then there is a, it gets dissolved, and then the material is available. So at once the entire piece of medicine goes to the intestine. That should not be happening. What is the correct way is slowly from stomach there should be release. So that is not achieved, okay, in the current medicines, whatever is available. You have Ecosprin, that is enteric coated aspirin. Ecosprin is enteric coated aspirin, but then it goes like that till intestine. So what is more meaningful is to coat micron or sub-micron size drug particles, powder, and then form a tablet. So that is more meaningful.
After the coating, you need to say.
So what I propose is each individual particle should be coated first, and then it should be put in the pallet forming to form a tablet. Current practice is tablet is formed and then the entire tablet is coated.
Yes.
So this is the current practice. So now let us see next.
But sir, nowadays the tablets are available. We have a drug in that, and that is with another layer, not coated. What it does, when it will go to the stomach, there is a reliever. It will make it in a living state.
But goes to stomach.
Yes.
See, some drugs if released in stomach, no issue. It is for those drugs which make adverse effect on stomach, or stomach environment make adverse effect on drug, for those enteric coating is essential.
Since that stomach environment is more acidic, I understand.
Yeah.
And
So
that's why that may harm.
So what are the requirements of enteric coating is, it should withstand at least 2 hours in stomach acid. Now normal stomach acid pH is 2.5 to 3. But if you want to test it, it should be tested at rigorous condition. If I am designing a carry bag to carry 5 kgs of potato, I cannot just design merely for 5 kgs. I have to test it for 7 kgs. Even while designing power supply, if I just want peak to peak 20 volts, I will be designing it for 25 volts.
Yeah.
Right? So same way, this is more acidic. pH 2 is more acidic. So should be tested at pH 2. Once it reaches to small intestine where pH is around 5.5, it should disintegrate within 12 minutes. Now if that coating remains there for few hours, what is the use? It will not be available for intestine for a longer time to absorb. Right? So it should disintegrate in a minimum time. Then coating material should not be harmful to the body or should not form complex with the drug itself. And the coating should be pinhole free and uniform. For example, say 90% part of that drug particle is coated and 10% opening is there, or some void is there, or some crack is there, it is possible that the stomach acid may enter through that and may damage either drug, or the drug is released in stomach may damage stomach lining, right? But not necessarily all drugs have this kind of effect. There are some safe drugs can be released in stomach and then can go to the intestine. That's not an issue. Okay, so pinhole free film is very important. Otherwise, that coating would not serve the purpose. And the process should be cost effective and environment friendly. That we should not forget. Next. So conventional coating methods have several drawbacks, and therefore we propose this. Next. Now here, this article we have published recently in 2021 in Journal of Drug Delivery Science and Technology, Pulse Plasma Surface Modified Omeprazole Microparticles for Delayed Release Application. Now here in this diagram, this is basically what I have put is all data, okay, in one slide. Pointer. Okay. So now this is omeprazole particles. Okay, I have shown one big and other small. Just I wanted to name here, so that's the purpose. Now this is plasma environment. We created plasma of methacrylic acid and methyl methacrylate, MAA and MMA, and the flow rate was 100 cc per minute and this 200 cc per minute, so that the stoichiometric ratio of MAA to MMA is 1:2 maintained. Okay. Then here the working pressure was 0.5 millibar in the rotating reactor and power was 45 watt. This is the plasma, okay, and the nanoparticles, okay, sorry, submicron size particles, okay, these OME were put into that, and then you can see that those particles are coated in the plasma, right? And we varied duty cycle. Initially for 5 minutes continuous wave plasma was operated, because if it is a continuous wave, the cross-linking would be better. And as we go on increasing the off time, okay, on time was kept constant 5 millisecond and off time was varied from 10 to 30 millisecond. So because of that, we could retain some functional groups from the precursor monomers, and this is the time of deposition, okay, for each kind of different kind of pulse. So variable duty cycle allowed us to deposit layered or graded structure. So the film chemistry was different for CW plasma, was different for 510 plasma, 515 is different, 530 is different, like that. So graded layer deposition was carried out. Then, you know, then these coated omeprazole microparticles, okay, then we prepared a tablet that you can see here, okay, this is the tablet. Now when such tablet is taken, what happens is that in stomach itself, the tablet is broken down and individual particles are separate here itself and they enter into the stomach slowly. Whereas if entire tablet or the capsule is coated, then that entire capsule you will observe here, and then you know it's available or it is binding on now intestine. चलो पूरा absorb कर लो, अभी एक ही टाइम पे दिया है, पूरा खाना खा लो. Okay, so that is not the correct way. So you know here in the stomach, these particles should get distributed, and with food, okay, they should come one by one like this, so that you know आराम से stomach can absorb this medicine. So here, you know, as soon as it enters into the intestine, okay, you can see that the coating is removed and now this drug is available for the intestine to absorb, and yet some drug molecules, okay, particles are there, okay, they are in the pipeline. This is what, okay, is the beauty of coating individual particles and then forming tablet, right? So here you can see that the pH is 1.2 and you know plasma treated is this one. So the release, this is percentage release. Plasma treated is not released much, whereas untreated is released immediately. However, when the pH is changed to this, of course these are the pharmacopoeia guidelines that we have to have this pH only for study. It's FDA protocol. And then here we see that for plasma treated, you can see that in 25 minutes around 80% of the drug is released in 25 minutes, right? So it's pretty well. The next. Similarly, we quoted aspirin crystal. Bare aspirin crystal was released immediately, whereas aspirin crystals coated with the pulse 1 millisecond on, 5 millisecond off, so that the release rate you can see. And further, this duty cycle we varied 1 millisecond on, 3 millisecond off. So it means that the film is more cross-linked, and because of that the release is slow, that we can control the release rate. So this is kind of a sustained release, and the drug is available for a longer time for absorption instead of 2-3 times a day. Okay, probably 2 times a day that drug would be sufficient because it's a sustained release kind of thing. Next.
Duty cycle variation है. It is possible only with electrical way of producing.
Yes.
Normally we cannot.
No. Electrically. We have that only. Because thermally you cannot vary temperature so fast. Next. This is another example just to show that how uniform coating is possible. For some application we wanted to have iron oxide nanoparticles coated with allylamine. So we wanted amine groups to be incorporated on the nanoparticle, and you can see the contrast. This is polymeric film and this is nanoparticle, and this is the scale 5 nanometer. You can see here 2 to 3 nanometer layer coating, and is quite uniform, that you can see. Next. Now here is just in order to visualize our experiment, what we did is we have coated red dye particles which are very strong. Even few dye particles, if they remain uncoated and if it is put in the water is going to change its color, right? So they were coated using perfluorohexane as a precursor in 360-degree rotating reactor, and here the pH in these two beakers currently is 2.5 pH, is acidic, and in these measuring cylinders the solution is there. So when we pour this solution here, the pH will alter to 5.5, right? Now here in this first beaker we are going to put uncoated particles. At the same time in the second beaker we will be putting coated dye particles, and it is tested at a rigorous condition that even the magnetic stirrer is put below this. So you can see that, because you have to taste it at a rigorous condition than whatever is in the stomach, right? Okay, next. No, you just click on that image, it will play. Now you see that uncoated immediately showed color. Just hold, stop, pause it. Now here, just assume that if 90% part of those particles were coated, or if some cracks would have been there, or not all 100% particles are coated, then this would have shown some color. But the coating, the quality of coating was so good that here you cannot see even trace color, right? And when we pour buffer solution, so that to adjust pH 5.5, what happens, see. Continue. It will. So pH is changed, coating is disintegrated, and you can see the it's released. Next. Similarly, we did work on enhancing solubility and hence bioavailability of drug ritonavir. Ritonavir is a drug which is used to treat HIV patients. The drug is also costly. The therapeutic effectiveness of a drug depends on bioavailability and ultimately on the solubility of the drug. Now, if the drug is not soluble, then its bioavailability is limited. Bioavailability is a term, what it means is that how much percentage of that drug the body is available for body to take, available for body to absorb. If the bioavailability of the drug is 50%, and theoretically, if say 10 milligram dose is sufficient, but bioavailability is 50%, so you have to have tablet of 20 milligram. Then only